Okay, 4. Okay. One of the most common applications of calculus involves determining minimum or maximum values. For example, what is the greatest profit? What's the least cost? What is the optimum size? Etc. So that's just some examples. That is known as optimization. Okay, finding the optimum solution for a problem. We can use calculus to find out what would be the optimum solution for whatever problem we're given. Okay, so I'm going to give you some guidelines that you can use for applied minimum or maximum problems. Okay, number one, and this might not make sense at first, it won't make sense until we actually do a problem, is to identify all given quantities. And quantities that need to be identified or determined. I would also make part of step 1 to make a sketch if possible. Drawing sketches for these problems can be very helpful if possible. Sometimes the situation gets rather complicated where a sketch would not be really a good way to go. But anything involving volumes, areas, anything geometric, you want to definitely make yourself a sketch. Okay? Step number 2 would be to write a primary equation for the quantity that is going to be minimized or maximized. Okay, so we're going to write a primary equation for the quantity that is going to be minimized or maximized. Why is it called a primary equation? Because there's going to be more equations involved in here. So the primary equation is the one that we're going to be applying the calculus to. In other words, we're going to have other equations that are going to help us manipulate the primary equation, and then we're going to apply calculus to it. Okay, but we definitely need, one of the very first steps is to identify what that primary equation is. Okay, step number 3 would be to reduce the primary equation to one variable using secondary equation. So we're going to reduce your primary equation to one variable using a secondary equation. Okay? Step number 4 is to determine a feasible domain for the problem. In other words, determine the values for which stated problem makes sense. So all of these are going to be real life scenarios, so you're going to have to really restrict your domain so that applies that problem. And last but not least, step number 5 is to use calculus techniques to find the min and max. In other words, what are you going to have to do to find min and max? What have we been doing? First derivative test, second derivative test, etc. Okay? So those are the 5 steps that we're going to use in order to optimize a problem. And what we're going to do is I have, let's see, 1, 2, 3, I have about 4 problems that we can do together, and then there's about 6 or 7 for homework. Okay? Yeah, this takes a lot of work, so each problem takes about a page. Cool? Alright. Do we need a little bit more time copying this down? Yes? Okay, so let me pause the video, and then we'll move on. Continue. Okay, we're going to start with something easy and then progress. Okay? So example number 1. What is the minimum value of x squared plus y squared? What's up? Half a page probably. Given that x times y equals negative 16. What is the minimum value of x squared plus y squared given x times y equals negative 16? Okay? Alright. We have 2 equations. Agreed? The primary equation is always the one that we're going to minimize or maximize, which in this case we're looking for a minimum, right? Which will be your primary equation then? So I'm going to say that my primary equation, I'm going to say, I don't know, S for the sum, right, equals to x squared plus y squared. Agreed? That's what I'm looking for, the sum, right? Okay. Step number 2 says, reduce the primary equation based on the secondary equation. We want to have this equation in terms of one variable. I'm not talking about the s for the moment. I'm just talking about what was given to us. We have 2 variables at the moment. Okay? Alright, sorry about that. So we have 2 variables at the moment, x squared and y squared. We want to keep this in terms of one variable. Typically, I recommend that you keep it in terms of x, since we've been so used to using x as far as derivatives, and it makes it a little easier. That's what I recommend. You don't have to. It should still give you the same answer. But what I want to do is I'm going to use this equation right here, the xy equals negative 16, to solve for y. So if I solve for y, y would be negative 16 over x. Agreed? Okay. What I can do then is I can take this and replace it for y. And that would give me one variable. Agreed? So then I would say s equals x squared plus negative 16 over x squared. Algebraically, I would suggest you simplify this before we start doing any calculus with it. So x squared plus 16 squared is what? 256. So 256 over x squared. Agreed? That's as far as I would take it. If you want to, you could also write it like this to avoid using the quotient rule, because we're going to have to differentiate here in just a second. You can write it as 256 times x to the negative second power. That way you can use the power rule instead of the quotient rule. You guys see what I'm saying? Okay. We got to determine some kind of domain. Are we going to have any restrictions on this problem? Do we need to restrict our domain? It doesn't say anything about positive or negative numbers, so we don't have a domain restriction here. Agreed? So that step goes out the window, which takes us to the last step, which is now use calculus to determine minimums or maximums, which in this case we are determining a minimum of this primary equation right here. Agreed? So then, we are going to differentiate in terms dx equals, what's the derivative of x squared? 2x. What's the derivative of 256x to the negative second power? Negative 512, right? Yeah, 512 x to the negative third power. Agreed? Okay. So you differentiate it. We're now looking for a minimum value, right? That's what the problem was looking for. What do? Why would you set it equal to 0? Critical numbers. In other words, we're going to have to use our first derivative test in order to find our min and max values. In this case, we care about the minimum value. Agreed? What I would do is, before I do that, I'm going to rewrite this as 2x minus 512 over x to the third, just because that bothers me a little, but should be fine. Okay, so we need to set this equal to 0. So 2x minus 512 over x to the third equal to 0. Suggestions. What do? So this is now just algebra. What would you guys do? So one of them, x would be equal to 0 because we would have undefined. Agreed? So one of our critical numbers will be 0. Okay, so this is going to be one of our critical numbers because we can't have 0. Alright, what else? What do? Take the what, I'm sorry? Okay, so then 2x equals to 512 over x to the third. Now what? So cross multiply, right? Okay, or you can multiply both sides by x to the third, same thing, right? So 2x to the fourth equals 512. X to the fourth equals 256. And then, how good are you with fourth roots? Plus or minus 4. Cool? Alright, so here's what we know. X equals 0 and x equals plus or minus 4 are both critical numbers. What can I do with them? Make yourself not a timeline, but a number line. And test the values. We need to figure out where we're having a minimum. Agreed? Okay. So, what would be a good value to test on this side? F prime of negative 5. Between here and here, I would probably choose negative 1 to keep it easy. Between 0 and 4, I would probably test 1. And between 4 and infinity, I would probably pick 5. Okay? Where am I going to plug these values in? To the first derivative, right? Do not go to the original derivative, which in this case would be right there. Agreed? Okay. So, if I plug in, let's start with 1 to make this simple. 512 divided by 1 is going to be 512, right? 2 times 1 is 2 minus 512. That's definitely going to be negative, right? Okay. If I plug in negative 1, negative 1 to the third power stays as a negative. So the moment I divide negative by negative, it becomes positive, right? And then this is going to be negative 2 plus 512. That's going to definitely be a positive, right? These two values, we're going to have to actually think a little bit more or be more careful about it, okay? If I plug in a 5, that's definitely 10, right? So we're going to have 10 minus something, right? Alright, what is 5 to the third power? 125, agreed? So 512 divided by 125. You don't really have to do the math there to know that this is going to be less than 10, agreed? So 10 minus something that's less than 10 is going to stay positive. On this side, if you have negative 5, right? So negative 5 times 2 becomes negative 10 minus 512 in this case divided by a negative 125, right? So it's going to make that a positive, so 125. Again, same scenario. This is not going to be more than 10. So if it's negative plus something that's less than 10, it's going to stay negative in that case. Agreed? Okay, so then now that I have these results, how can I answer the question? What do I know using the first derivative test? What did I just find out? What's happening on this interval? Decreasing, and then you begin to increase, and then decrease, and then increase. So what happens when you have decreasing and all of a sudden you turn into increasing? What does that mean about this value right here? That is a minimum value. Agreed? Here, if you go from increasing to decreasing, you have a maximum value, and here you have a interesting. So I have two different answers. Does this mean that x equals negative 4? Agreed? Isn't that the x value? And isn't this x equals positive 4? Well, how can I use the beginning equations to figure out what y is? Would I use the primary equation, or would I use the secondary equation? You have to use the secondary, because you're looking for a sum. You don't even have a sum, right? So we need to use this equation to figure out what y is. Well, this problem becomes very simple. If x is positive, so we can say 4 times y equals negative 16, then y would have to be negative 4. Agreed? But if x is negative, so we can say negative 4 times y equals negative 16, then y would have to be positive 4. So we have two different scenarios. Therefore, x could be plus or minus 4, and y could be plus or minus 4. Agreed? And the sum of x squared plus y squared would be what? Not 16. What's 4 squared? Plus 4 squared? 32. And that would be your solution. Okay? That will be the values that would give you a minimum sum. Because there are, like, if you think about it, we could have tried to do this without calculus. Like, we could have said, okay, there's two numbers that give us 1 times negative 16, right? And then 1 plus negative 16 is negative 15. Agreed? And then you have, you had to square those, and those numbers would have been a lot bigger, right? And then you could have tried 8 and negative 2, and so on, but then you never really thought about what if there was decimals in there. There's still a way that we can multiply decimals to get this. So this problem can be very difficult if we try to guess and check. As opposed if we use calculus, this can be a very simple process. Okay? Questions over this very first problem? Awesome. Alright, then let's step it up. Let's throw some geometry in here. Ready? Example number 2. A manufacturer wants to design an open box. This is important. Open box having a squared base and a surface area of 108 inches square. Okay, so that's the material that he wants to spend on this box. It needs to have a square base, and it needs to be open. what dimensions will produce a box with a maximum volume? Okay, so a manufacturer wants to design an open box having a square base and a surface area of 108 inches squared. What dimensions will produce a box with a maximum volume? This time, no equations were given to you. So you're going to have to come up with your own equations for this problem. There are some hints on the problem so that you know what equations to look for. What is the quantity that we are looking to maximize? The volume. So somehow, some way, I need to find a volume equation. What else was given to you? So I'm going to assume then that we're going to have to figure out what surface area is. Okay? Now, before we start this problem, sometimes it's very helpful to draw a sketch. If you want to square, I mean, you don't have to be an artist, but let's pretend you want a square base. So there's my square base, and there's my box. That's the best I can do. Okay? Sort of. I'm sorry. Try my best. Okay? This right here is open. So there's no top on the box. Cool? Help me out here. If the square is going to be base, if the base is going to be square, the dimensions have to be the same, agreed? And then that would also be x to make it a squared base. What else will we need to find out in order to find the volume of the shape? So are we okay with calling it, we can call it h, that's fine, for height. Cool? Alright. Using that diagram, what will be the equation for the volume? X squared h. Agreed? Because the volume of a rectangular prism is length times width times height. Cool? Alright. Then the question becomes, we need to find surface area. An equation for it. Do you guys remember how to find the surface area of a square prism in this case? Yes, I agree, but you have to be careful because we don't have a top. So here's my suggestions. We have one base, agreed? We need to find the area of that base. So the area of that base, do you guys agree whether it's x squared? Right? Plus, we need to find the area of each one of the sides. Okay? Each side, the area of it would be x times h. So how many sides do I have all around? So 4xh. Agreed? I have two equations. Which one is the primary and which one is the secondary? Why is that the primary? Exactly. The primary is always what you're trying to maximize. Okay? Now, there was some information given to you on the problem. So before we even go any further, we know that we have to change this formula from being x squared h to having just x's. Agreed? So we're going to have to use the secondary equation. However, the problem gave you the surface area. So what if instead of saying surface area, we say 108 equals x squared plus 4xh? Agreed? Okay. How can I then make this equation in terms of just one variable? What do I need to do with this equation? Solve for what? H. So if I solve for h here, do you guys agree that that would be h equals 108 minus x squared divided by 4x? Right? Okay. Now that you have h, you are going to plug it into that formula right there. Okay? So volume equals x squared times 108 minus x squared all over 4x. If I'm going too fast, let me know so I can slow down. Okay, before we begin to do any sort of calculus in this, remember that we talked about setting domain restrictions. Agreed? We're in terms of x. You guys with me? If I'm looking at this problem, in order for me to have a box, what is the lowest value that you can have for x? We can have it even lower than 1, right? We can make decimals, right? Greater than 0. Agreed? X has to be greater than 0. You guys with me? Otherwise, that won't be possible. That would be impossible. We can have 0.0001. I mean, like, that would be almost impossible to produce, but it's technically, mathematically, still possible, right? But what's the highest that x value could be? So, yeah, we have a restriction because of the surface area. Well, the biggest box per se we can use with that material would be if it had no height at all. Agreed? So if it had no height at all and our base is squared, then remember that surface area would be in this case just x times x, which would be 108. So x squared equals 108. Therefore x is square root of 108. That is the biggest. Using that material, we would have no height. It doesn't create an actual box. It's just the actual just flat sheet of paper or cardboard or whatever we're using. Agreed? Okay. That gives us some restrictions, and they may be helpful for when we have our minimums and maximums. Okay? Now, we're ready to do some calculus here. Okay? What do you guys suggest I do to make this problem easier? Because as it stands right now, I have product rule and quotient rule. I would distribute the x squared. Yeah, that way if you distribute the x squared, then you can take out the x from the... Okay, so then you're saying 108 x squared over 4x minus x to the 4th over 4x. Right? And that simplifies to be volume equals 108 x over 4 minus x to the 3rd over 4, right? One you kept it. That's fine. One more thing you could do here is maybe what's 108 divided by 4? It'll be what? It's a nice whole number. Okay? But if you didn't see that, it wouldn't make, like, the calculus would not have made a difference. Okay? You guys okay with that? Now, if you need to rewrite it like this, it's absolutely okay. Would that be the same thing? Right? The reason why I did that is because then it makes differentiation a lot easier, right? So, dv dx, we're differentiating in terms of x, equals, what's the derivative of 27x? 27. And what's the derivative of 1/4 x to the 3rd? Well, negative 3/4 x squared. Agreed? Now, there's your derivative. You're ready to apply the first derivative test, which we're going to then set this equal to 0. So 27 minus 3/4 x squared equal to 0. Okay? You guys okay if I multiply everything by 4 so that I can get rid of the fraction? Right? So 4 times 27 is 108. minus 3x squared equals 0. Then we can say that 3x squared equals to 108. Agreed? Okay. Which means that x squared equals to 36. Yes, 36. Which means that x would have to be plus or minus 6. Agreed? What's up? X cannot be 0. Remember we said that our domain restraints, otherwise you wouldn't have any material. Right? Okay. Here's my question to you. If we have x values of negative 6 and x value of positive 6, can x be negative? Which makes our life easier. We only then have one value to test out. That's the whole point of us setting the domain restraints, to avoid doing extra work. Could you have done the extra work? Yes. The problem is that some of you guys will get caught up with doing the math that are not going to pay attention to the problem, and you're going to give it as a solution, which would not make sense. Okay? So then, we have the value of 6. I would test out some values. I wouldn't test out 0 in this case. I would probably just pick 1, something greater than 0, and then maybe 7. Okay. If we go to the derivative, which is right here, first derivative, and I plug in 1 in there. 1 squared is 1 times negative 3/4. It's negative 3/4. 27 minus 3/4 is going to be positive. Agreed? Okay. 7 squared is 49 times 3/4. Well, we know 50. If we take a fourth of 50, it's about what? So we have 3 of those. Is it going to be bigger than 27, guys? Yes, it is. So 27 minus something bigger than 27 is going to give us a negative. So then you then realize by the first derivative test that if you're going from an increasing to a decreasing behavior, you have a maximum value. Or I'm sorry, max value here, so x would be 6. Now, we need to find out what the other dimensions are, and we need to figure out what that volume is. Okay? So now we know that x is 6. How can I figure out the rest? Well, remember how we had this function right here? The 108 equals x squared. Can I plug in x in there to find out what the height is? We sure can. So I'm going to say 108 equals 6 squared plus 6 times 4, which is 24 h. 108 equals 36 plus 24h. 24h would be what? 72? And h would then have to be 3. Agreed? Pardon. So here's what we know. Therefore, the height would have to be 3. The length would have to be 6. The width would have to be 6. Right? And the maximum value, or the maximum volume, I'm sorry, would be 3 times 6 times 6, which would be what? What is it? 108 inches cubed. They do, right? It's a lot of work, though. It's a lot of concept to connect. Okay. Alright, how are we feeling about them? We're good? Alright, I want you to try one. I'm just going to read it to you and then you try it. And then I'll have one more from you and then that's it. Okay? Alright. No. But you could use trig in here, why not? Alright, here's the problem. Let me explain it to you. You have a cardboard. Okay? We're going to create another box. Cool? It's not going to have a top once again. But this time, you're going to actually cut out. And I want to make sure that what you cut out is squared. Okay? So if you cut out 1 unit here, then you have to cut out 1 unit up. Okay? The material as it stands. So if I'm giving you a flat sheet of cardboard, it's a 30 by 20 cardboard. Okay? I want to create a box with a maximum volume. What would the dimensions have to be to create that maximum volume? I'll let you think about it for a while, and then if you can't get started, at least I'll give you starting points, and then you can work it on your own. Cool? So think about it for a while. Okay, so for the box, we talked about how if this is your flap and you're going to cut X distance from both sides, so the distance from here to here would then be 30 minus 2x, this one would be 20 minus 2x, and then the height would be your x because that's when it gets folded up. Therefore, the volume would be x times 20 minus 2x times 30 minus 2x. There's a couple things you could have done here algebraically before differentiating. All I did was, rather than having 3 products, I just distributed that x to get just 2 products. You could have distributed this out and then you would just have power rules. Honestly, I don't think either one would save you a lot of time, so what I did was just to practice my differentiating skills. I used the product rule, so the derivative of this would be 20 minus 4x times that, plus the derivative of this. Did I just make a mistake in here? No, I didn't, sorry. The derivative of this times the derivative of that, which is just negative 2, I'm sorry. Cool.
Wait, why did you put less than or equal to 0?
You're right, it should just be less than and less than. Okay, good catch, sorry. Okay, the domain, the way I figure it out is that we all understand it has definitely be greater than 0, right? Like we can't have 0, otherwise we don't have any material. Agreed? But here's what I know. I need to look at this shorter side, the 20, to figure out what's the biggest x could be, because x is the amount of cardboard I'm cutting out. So remember that if I cut 1 unit from here, then I have to cut another one from the other side, eventually getting to the midpoint, which is 10. So I did that algebraically here. I set it equal to 0 and then I solved for it, so we see the 10. After you differentiate it, I got this mess right here. 12x squared minus 200x plus 600. You gotta set it equal to 0. I use the quadratic formula, so what I did to have smaller numbers, I reduced, then I use the quadratic formula. Okay? I found the 0. There's 2 zeros, but the one that would work for this domain would be this one right here. 50 minus 10 root 7 over 6. And then I plugged in some values and I got that it goes from increasing to decreasing, so there will be a maximum at this point. So then I figured out, I went for the length, I plugged that into the length, the width, and the height. So that's what I got for the length, the width, and the height. Therefore, to find the volume, you multiply all those 3 together and you get 1056.306 units cubed. Okay? That's that. homework is on the hub. There's other problems that we'll post on along with it. So there was another problem here that I did. It'll be on the notes on the hub if you want to look at it. Cool. All right, that's all I got for you today.